Let's talk about the Lewis acid-base model. In the Lewis acid-base model, we explain and define an acid and a base using electron pairs. So this is a different way of thinking compared to the Bronsted-Lowry model or the Arrhenius model. And so this is like a whole separate room where instead of defining acids and bases in relation to water, protons, we're thinking about electron pairs. So in the Lewis model, an acid is an electron pair acceptor. And I remember that because acid and acceptor both start with A. I don't know if that helps you. And a base is an electron pair donor. And so in this aluminum example, we can see that the aluminum is a Lewis acid because it's a cation. So it is electron deficient. It's ready to accept electrons. Those electrons come from the lone pairs on the Lewis base, in this case water. Water has lone pair electrons, so it can be the Lewis base, the electron pair donor. And we think about that electron pair going from the Lewis base to the Lewis acid. And we see that we can have that happen several times. So we can get all 6 water molecules around aluminum. So we can have that happen with nonmetals as well. Here we've got the Lewis acid BF3, and it can accept an electron pair from the Lewis base, the F- ion, and in that way form what we call a Lewis acid-base adduct. So adduct comes from the Latin. Ad usually means together, and duct is like lead. And so these are led together, smushed together, combined. So the adduct is the combined version of this. Okay, so let's practice. What is the Lewis acid in this reaction? In this reaction, we would say that the Lewis acid is the silver plus ion, B. And that's because if we draw a Lewis structure, same guy, of NH3, we see that it has a lone pair. So this is going to be the Lewis base. Silver has no lone pairs. It is a cation, so it is going to accept electrons from the Lewis base. And then instead, this silver with 2 ammonias thing, this is our Lewis acid-base adduct. Now sometimes with transition metals, we use some slightly different words here. For a transition metal, we might say that silver is the metal and ammonia is the ligand. And that together, those make a complex or a coordination complex. And so you'll see both of these terms, and you can see that the idea of a ligand and a metal makes a complex is kind of interchangeable with this idea of a Lewis base and a Lewis acid make an adduct. So why do we even have this model? So here is a picture of G.N. Lewis, and why did he want to think beyond the Bronsted-Lowry model? And so here's something from Lewis. We are so habituated to the use of water as a solvent, and our data are so frequently limited to those obtained in aqueous solutions, that we frequently define an acid or a base as a substance whose aqueous solution gives, respectively, a higher concentration of hydrogen ion or hydronium ion, or of hydroxide ion than that furnished by pure water. This is a very one-sided definition. So Lewis wanted to be able to talk about what happens to ions that aren't in water. You can't have a proton donor and a proton acceptor in a solvent that doesn't have protons. So instead, by switching around to thinking about electrons, we can explain more behavior. So the Lewis acid model in that way becomes more general and kind of more inclusive of different kinds of behavior. So which one should we use? Should we use the Lewis model because it's the most inclusive? Should we use the Bronsted-Lowry model? Should we use the Arrhenius model? The answer is we're going to choose different models for different situations when they help us to explain whatever behavior we're seeing. If we're in water, the Bronsted-Lowry model is still one of the easiest and sort of most straightforward to use. So we're going to keep the Bronsted-Lowry model when we're in water. But we can also remember that the Lewis model still happens, and it can help us explain some behavior. So here, we can see that the Lewis acid-base concept and the Bronsted-Lowry acid-base concept can kind of coexist. So we said before that this aluminum complex represents the combination, that this is the adduct of a Lewis acid and a Lewis base, water, donating electrons to aluminum. Now, we also said that hydrated metal cations are acidic, and we meant Bronsted-Lowry acidic. And so you can see how that works, where in the presence of the Lewis acid, the Lewis base water is disposed to give up protons to form the conjugate base, which is the aluminum with an OH- ligand. We can put a Ka value on this reaction because we have an acid plus water goes to the conjugate base plus H3O+. And so we see here how the Bronsted-Lowry model and the Lewis model can kind of intersect, but they're telling us different things. The Lewis acid-base interaction is sort of within the aluminum complex, whereas the Bronsted-Lowry acid-base part is in thinking about how that aluminum complex reacts with water.